So, my name is James Roper. I work for a company called Lightbend. If you haven't heard of Lightbend before, we used to be called TypeSafe. We renamed ourselves about a month or two ago. We're the company that are kind of the stewards of Scala and a number of other frameworks built on the JVM, including Akka, Play Framework, and most recently Lagom. And my role at Lightbend has been the tech lead of Play, and now I'm also the tech lead of Lagom. So today's talk is Rethinking REST in a Microservices world. I'll give a very quick spoiler. In the title of the talk, I've taken aim at REST a bit. As you'll see in the talk, REST isn't a bad thing. It's more our attitude and how we kind of just go straight to it all the time that's the problem. So just before you think I'm saying, everybody, we've got to switch away from REST now, don't do REST anymore, that's not what this talk is about, and I don't want to hear anyone saying that that's what I'm saying. So today we're going to look at what is asynchronous communication. And really this talk is about asynchronous communication. It's about synchronous versus asynchronous and what that means. And particularly it's about our architectures. I'm not talking at the micro level, I'm talking about whole systems architectures. And we're going to see some demos of how asynchronous communication looks in practice in perhaps not a real system, because showing a real whole system would be huge for a presentation, but something that you can hopefully relate to and see how it might apply to the systems that you work with. So let's start with looking at what is asynchronous communication. So the first thing that I want to say, and I really need to make this point strongly, is that I'm not talking about asynchronous IO. Anybody here familiar with kind of the reactive manifesto, the reactive movement? So a lot of the things associated with reactive are often also asynchronous IO. And while what I'm talking today is very much about reactive, it's at a much higher level. So asynchronous IO is good, it's really great. I try to do everything using asynchronous IO. But it's just not what this presentation is about. So just so that you know what asynchronous I/O is, it essentially means not consuming threads while waiting for things to happen. Okay, so I've got some Java code. We're going to be looking at mostly Java today, but the concepts that you learn today are applicable to any language. We can see some Java code. You can see we've got something that makes probably a web request there. It returns a completion stage. If you haven't come across completion stage before, this is the Java 8 equivalent of promise in JavaScript or future in Scala. We make, and rather than, if we want to say convert the response from this service that we're calling into something called my model, rather than waiting for that to happen then executing it, we attach this callback which says, take the response, decode it into my model and return the model. And so this callback here in red, that will only take a thread when it's executed. It's not going to wait for that to happen. So that's asynchronous IO. Okay, but that's not what this presentation is about. You could sum up asynchronous IO as being about not blocking threads. So what is asynchronous communication? In the high level that I'm referring to, asynchronous communication could probably be summed up as saying not blocking requests. It certainly could be defined a lot broader than that, but for a useful definition for what I'm talking about today, that's what we're talking about. So a service that's processing a request from another service or from something else shouldn't block on another service. And when I say block, it shouldn't require waiting for this other service to produce its response before it sends its response. So let's have a look at what synchronous communication in contrast might look like. We've got our user here, fairly happy. user makes a synchronous request to A. I've used the double arrow there to say, there's a message that goes to A and a response that comes back. Okay, so that's what synchronous communication is. You send a request and you get a response back. Asynchronous, there's just, you send a message and nothing happens. Well, something happens, but you don't necessarily hear about it. So in order to fulfill this request that the user's making, service A has to make a synchronous request on service B. Similarly, another one to service C, another one to service D, and it might not be all linear, there might be another one to E, and E also might depend on D. Okay, so if all these services are up, if they're all responding and happy, our user will get all these responses, requests and responses will be made, our user will get them back, and our user will be happy. But what happens if, for some reason, D isn't working? Maybe it's gone down, maybe it's overloaded, or maybe it has actually exploded. Well, since C and E, they're still running, they're fine, okay? And especially if they're using asynchronous IO, so they're not blocking, they don't have threads that are blocking waiting for this stuff, they should still be quite responsive. But because they're depending on service D in order to fulfill their requests, they may as well be down. Okay, they're still returning errors because they can't handle that. And likewise, B and A are also down, and effectively, this whole system is down as far as the user is concerned from the point of view of making this request. So we don't have a very happy user. So the problem with synchronous communication is that when there's a problem, the failure bubbles back up along your synchronous pathways. Okay, we saw a synchronous pathway goes one way, but the failure will bubble back up the other. Okay, and back to the user. Okay, not just failure, but slow response times. If all your communication is synchronous, the fastest that your service can respond is as fast as the slowest service that it synchronously depends on. So if service D might not have been down, it might have just been slow because it was overloaded, it would have meant that the user got a slow response, no matter how fast the rest of the system was. What you end up if you use synchronous communication everywhere is you end up with a situation where you have some services that are needed by everything. So a common example of this would be, some sort of authorization service, or if you have some sort of service that has entity relationships that then are then used for authorization. And so every time you need to do an authorization check, you have to go to this service to check for if this is allowed to be done. Okay, and that means that particular service is a bottleneck to load. So as long as that service is slow, the entire system is going to be slow. And it's also a single point of failure. If that service goes down, your whole system goes down. And if you're really using synchronous communication everywhere, you end up with a situation where the whole system needs to be up to serve any request. And if you've got this system where, one system dictates the responsiveness of the rest of the system, one system dictates whether the whole system is up, and the whole system essentially needs to be up to do anything, basically you're just describing a monolith there. You may have divided the entire system up into lots of microservices, but the fact that it's still behaving like a monolith. So let's have a look at a contrast with asynchronous communication. So still user A, our user makes a synchronous request with service A. But that's all that needs to be done. That service A just returns the response and the user gets it and is happy. But the question is, before we saw that A actually does have a dependency on all these other systems in order to be able to serve the request, how does it get the data and everything that it needs to know in order to serve that request? Well, here's our system D over here. Let's say some sort of event happened here, maybe there was an order or something that was submitted or something like that. Well, it publishes its events and they go to systems C and E. And I'm not sure why there's lines across here, some sort of rendering error. And similarly, these C and E sends events to B and A, and A is able to receive those events, adjust itself accordingly so that it can respond to the user's request. And it's able to serve the user's request. Now what happens when system D goes down? Well, system C and E, they're both dependent on D for their data, but because they're not actually making a synchronous call, they're still able to service requests, so they're still up. And similarly, B and A, which are dependent on those systems for their data as well, they're still up. And so our user is still able to make requests to A and get some sort of response out of A, and so they stay happy. So with asynchronous communication, failure stops at the failed component. Okay? Instead of the synchronous thing where the failure bubbles back up, that failure is contained and the rest of the system is still able to be responsive. Slow response times likewise stop at the slow component. Okay, if system, let's say system C back here was slow in responding to requests to the data coming from D, it wouldn't impact whether A was still able to service a request or not. So this removes bottlenecks and single points of failure. So our system D, even though everything's dependent on it for their data and their information, it's not a bottleneck. It doesn't, of course it matters if it goes down, but it doesn't matter as much. The whole system isn't down just because it's down. But the problem here is that consistency may lack. So, and this is something that needs to be taken into careful consideration. And what makes distributed programming harder in general is that you don't necessarily have a consistent view of the world. So you can, however, design it to be eventually consistent, and we're going to see one pattern that can be used today in how to ensure that your systems are not just eventually consistent, but actually quite strongly consistent. And components are isolated. Okay, and when we're trying to do microservices, the big thing that people say about the advantages of microservices and why you should use them is isolation. And if you just take your services and not really think about the architecture and have different services, sure, you've got isolation between teams and between code. You may be able to have some technology isolation, things like that. Unless you use asynchronous communication, you don't end up with any of the architectural advantages of isolation. So what does this have to do with REST? I titled this talk Rethinking REST in a Microservices World. I've shown you how this is really about synchronous and asynchronous communication, but where does REST actually come into it? So REST is a synchronous messaging protocol, okay? It's built on HTTP. I'm specifically referring to REST as in implemented pretty much everywhere. The kind of higher level abstract definition of REST could be anything. But REST, as people commonly implement it today, HTTP using JSON, is a synchronous protocol. The client sends a request, an HTTP request, get me this, post this, here's a body, and the server sends a response. It's got a status code, some headers, and a body. It can be used for asynchronous messaging, okay? There's no reason why you can't use REST for asynchronous messaging. And the simplest example of this is actually built into HTTP itself, the 204 no content response code. So if you send the 204 response, you're not sending, it's actually the HTTP way of saying, hey, I'm not actually sending you anything back. And if you were making a call from a service to another service that was returning a 204 no content response, unless you actually wanted to have a synchronous dependence in there, if you're using an asynchronous framework, you could just fire that call and then forget about it. Essentially, then you've got asynchronous messaging. So REST isn't really the problem here. And so again, I want to say REST is not a bad thing. So let's say we have a system and it's a monolith. It's actually a really cool social network. It's called Chirper. It's so much better than some of its competitors. You may have heard of something called Twitter. Chirper is heaps better because I wrote it, and hasn't been deployed yet, but I'm sure it'll scale. So we've got this monolith called Chirper, and we've realized, hang on, it's a monolith, and monoliths are bad. You know, we've got to go to REST. Everybody's doing microservices. Let's convert it to microservices. Okay, so here's our monolith. We've got some components in it. We've got a friend service, a chirp service, life service. That's just the name of the components. These things make method calls to each other. You know, the like service makes a method call in the friend service because it needs to check if the person is friends with them before they can like it. The chirp service needs to get friends so that it knows which chirps to return to the user, and chirp service needs to go to the like service to get the count of likes on a chirp. And we want to convert this to a microservice, so let's get rid of that monolith. Okay, but our friend service, chirp service, and like service need to live somewhere, so we'll create a friend service, microservice, chirp microservice, like microservice. And we've got these communication pathways. Okay, so at the moment they're just direct method calls, but since they're in different services, they can't be direct method calls now, so what are we going to do? Well, let's just use REST. It's great. Replace all our direct calls with REST, synchronous REST calls. And so now we have our microservice and a system, and it should all be working fine, except that one day this friend service goes down. Okay, now since the like service and the chirp service both depend on the friend service for what they need, they effectively appear to be down now. They can't fulfill their requests. And so effectively, we've got a monolith. The whole system's gone down. User's not happy, user goes down. So if you're converting a monolith to microservices, the problem is that REST, in many places that I've seen, REST is used as a go-to. It's the default. So we had a call here, let's just replace it with a REST call. When you move into microservices, don't just do a one-to-one service interface replacement, okay? It's not, microservices isn't about just splitting those components into little services. You do that, you get all the complexity of having multiple services without any architectural advantages. So instead, you need to design an asynchronous architecture. So what does that actually look in practice? Okay, I've showed you some, services A, B, C, D talking to each other, but that doesn't really, it's all good and well to talk about and to say, but does that actually apply to the systems that you're using? Can it really work? So today, distributed systems is a huge topic. I can't possibly hope to tell you about everything about how a distributed system with asynchronous communication should work. But I'm just going to look at two approaches today. The first one is to denormalize and push data. And so you saw that kind of the high-level example of that before in the diagram. And the second is to communicate through the client. Okay, so instead of synchronous communication, effectively remove all communication altogether. The data is made asynchronously available by virtue of the fact that the client already has it. So denormalize and push, what does that mean? Okay. It means that services store all the data they need to service a request from the user. So in a normalized system, for those that have studied normalization, a normalized system, each bit of data only appears once in the system. And so it's very easy to know what the canonical version of the data is. But when you denormalize, you start to repeat data around the place. So service A will have more than just the data that service A kind of manages. It might have some data from other services as well. And somehow that needs to be kept in sync. because this data is now replicated and needs to be kept in sync, we need to address consistency. So what happens, sure we can push this data around, but what happens when two systems are answering with different answers? What happens when the data push fails or something is down when you try to push the data and it's not able to handle that anymore? Is it going to stay out of sync forever? And the approach we're going to look at today is to implement at least once messaging and idempotency. So for those that haven't come across idempotency before, it simply means when you can process the same message multiple times and the system will be in the same state no matter how many times you process it. By using at least once messaging, that means if the system goes down, and let's say there was a message in flight at the time, you can replay it. You don't know whether that message was successfully processed or not. There's no way to know. So what you can do is just simply replay it. And then as long as the message processing is idempotent, that's fine. So let's have a look at our, I've written our microservice and we're going to see this very soon. This is how it currently looks. When you go and get the chirp stream, so this is not what their calls actually look like, but conceptually you can think the user goes and gets the chirps. It makes a synchronous call on the chirp service, and currently that's making a synchronous call on the like service to get the number of likes for each chirp. So that in the feed you can see how many likes there are. So what happens when the like service goes down? Well, since the chirp service for that call is synchronously depending on the like service, that means the chirp service goes down too. You're no longer able to supply the app's core function. So what we're going to do is we're going to change this. I'm going to get rid of that synchronous communication, and we're going to replace it with an asynchronous push of the like count. So every time somebody likes a chirp, the count of likes for that chirp is going to be pushed to the chirp service. Now, because we're pushing the like count and not the fact that the user liked it to the chirp service, we can implement idempotent messaging, okay? Because as long as we process the messages at least once and in order, we can guarantee that the most recent like count message that we received will get the system into the right state. So you could pass all these like count messages and then you could pass the whole lot again and the system should be in the same state or it will be idempotent. This means if the like service goes down, those like count messages will no longer be published. Our chirp service may get a bit out of date, but that's probably not a big problem to see different numbers there, as long as eventually it's correct. And so it stays up and our user stays happy. So now we're going to get on to the practical aspect of this talk. So chirp has been implemented using Lagom. Lagom is a new microservices framework. It's open source. It's reactive and it's on the JVM. Currently it has a Java API and we are currently working on a Scala API as well. Lagom has first-class support for asynchronous messaging, and it's very restrictive, I guess, in the way that it guides you to do things. Although you can still pretty much do anything in it, the main APIs don't really, you have to kind of go to low-level APIs if you want to do some things outside of what it's designed to do. The main APIs kind of guide you into being very asynchronous. It provides a high productivity development environment, so you make a change in any service and that service will get reloaded and you'll be able to see that change almost immediately. And another feature of Lagom is it guides you all the way to production, so it has all that production tooling for helping you to manage a complex multi-service environment, including being able to, okay, I want 10 instances of this node, and having those nodes know about each other so that they can communicate each other using clustering and things like that. So let's have a look at this demo then. So first thing I'm going to do is I'm going to start Chirper. I'm in the SBT console here. I simply run all, and it's going to run all my services. Chirper will bundle a Cassandra database for you. That's what's provided out of the box, and so you don't need to worry about running your database. It's just there for you. It'll start a service locator, a gateway, and you can see it's compiling some stuff, and now it's started all my services. You can see they're all running on different ports there, but they're all accessible through the service gateway, so I can just access them on the service gateway port, which is 9000. So let's see if our system is running, and there it is. So you can see I'm already logged in as Bob, and there's a few tweets. I can say something else. And that's there, and I can like my own tweet. And that's pretty much what this social network does. Very simple, much better than Twitter. Just a few points here. So what you're seeing just here is a summary of the likes. When I click on the likes, it goes to the like service and to actually get a list of the users that liked it. So let's have a look at how that summary of likes is implemented. So I'm not going to go too deeply into this source code here, but it's using Arca streams to aggregate all these tweets together. They're actually pushed to the client as soon as they happen. And so this is concatenating the recent chirps that it's loaded from the database with ones that are newly published. And then it maps those to update the likes on each one. And this is a synchronous call. You can see here, it goes and makes a call to the like service, get likes, invokes it with the chirp ID, and gets the likes of, then returns the number of likers. So what that means is, let's say our like service goes down. Somebody accidentally set a flag called true in its configuration file. And if we come here, we should see that change gets detected and reloads. And so now, when we hit refresh, our feed's disappeared. Why has our feed disappeared? Because it was going to our like service. We can actually go here and look in the logs, all these exceptions, transport exception killed. Our service was killed. It's returning 500 errors, and our user's not very happy because, well, I wanted to see the chirps. So let's just unkill that for now. And I've done some preparation work already for how to do this. Now, probably the best way to implement this would be to actually use a message broker, for example, Apache Kafka. That will give you, out of the box, at least once messaging. But I'm actually going to use something a bit different today just to demonstrate how at least once messaging can be implemented. And actually, it just happens that this mechanism actually takes a few seconds to propagate messages, so you'll actually see it being eventually consistent. So on my like service, in Chirper, you define these service interfaces. I have defined a service call that basically returns a stream of likes, and the likes is a chirp ID, the number of likes on it, and also an ID of the event. And that event ID is very important, as we'll see later. So this is just the descriptor down here saying how it's accessed. And I haven't implemented it yet. So let's go and implement it right now. So I'm going to return an immediately completed feature because I'm returning an asynchronous stream, so I don't need to do any work up front. Chirper out of the box gives you event sourcing with CQRS, and what I'm doing here is getting the stream of that of those events directly. So all the like events that happen, I'm passing the like event tags, I'm getting from the stream. Now an important thing here is this offset parameter. So this offset is the ID of the service call. It's a UUID that actually, back in our service descriptor, we just find that to be passed as a parameter. And so anything that calls this can get all the events, can subscribe to all the events since that offset. And by doing that, we can ensure at least once messaging, because as long as we remember the last event that we successfully processed, we can get all the events that happened since. So that's not what I wanted. So now we're going to ask the, all these like events are simply this user liked this. They don't actually have the counts, we need the counts. So after getting a like event, we're going to actually go to the like entity and ask the like entity for the likes. Sorry. Actually, I'm missing something here. What I should have done is, we need to map all those events to go to the like service. And then we can, no, should have done this one. So this is Stream's code, map async. So I'm going to do up to 2 requests at a time, and that number is not that relevant. Then we're going to go and get the entity for the ID of this like event, and ask it to get the likes for this event, and then we'll map that to return this likes thing, which has the chirp ID, the number of likers, and the ID of the event. This, by the way, this event stream here is returning a pair of the event that happened. That's the first thing. So we can say that's the like event and the ID of the event. Okay, so we've implemented our service call. Now we need to consume that from our chirp service. So first thing I'll do is I'll go and remove these map calls from here to update the likes, because they won't be needed anymore and they're our problem. Now I've actually already implemented the database support. So this is a Cassandra code, looks somewhat like SQL. Important thing to note here is I've created this likes offset table. Every time we successfully process a like, we're going to store the UUID of it so that we can then get all the likes since that later if we need to. Down here, and so you can see it doing that here, here's the update, and then once that's complete, I insert into the offset table. And here is where I go and get the offset. So to actually do this subscription, I'm going to use an actor. And so the first thing I'm going to do is I need to get that offset that I'm at. And then with that offset, I can then go and get that count stream that we just implemented from the like service. Now I need some completion handling here. So when I get that stream back, if it was an error, then I'm going to send an error to myself. So this is an actor. I send a failure message, and you can see when I get that failure message, I simply throw an exception. And we'll see why I do that later. And I really should remember where I'm up to. Okay, but if it was successful, then I've now got a subscription to those that count stream. And so first I'm going to map it to update the chirp likes in the DAO. You saw that I'd implemented that before. And finally, I need to run that subscription. I'm going to send everything from that subscription to myself. And the reason why I do that is because that means if there's any failures, I get them sent to myself, which I can then kill myself as an actor. And finally, when the last, this this actor F sync needs to know what the last message to send is when the stream finishes, and if the stream finishes, it shouldn't finish because this is just getting the stream that never ends. So if it does finish, I'll send a failure message so that I kill myself. Now, what I now need to do is set this up so that when my service starts, I'll be able to run and maintain that subscription. So when you create an actor, the first thing you do is you create a props for that actor, which describes everything about the actor. It says, this is how it's created, these are the properties for the actor. So here's the props for that actor that I just implemented. And I'm going to wrap that in a back-off supervisor. Akka is designed around hierarchical failure handling, so you don't handle failure generally in an actor itself. The actor usually should just crash and then let its supervisor handle the failure. In this case, I'm using a back-off supervisor, so the supervisor will restart it after 3 seconds, but because it's a back-off supervisor, it's going to exponentially back off. So then, after 6 seconds, after 12 seconds, and so on. For a maximum of 30 seconds. So once it reaches 30 seconds, it'll keep doing it every 30 seconds. And so that way, if I have multiple nodes here, I won't be hammering the back-off supervisor. I won't be hammering the service. As it happens, the way I've implemented, I don't actually want multiple nodes. Because I've only got one stream, I haven't partitioned it up so that multiple nodes can consume it. I only really want it to be processed on one node at a time, otherwise I'm just doing excess work. So I'm using the Arco cluster singleton pattern, and that will ensure that no matter how many nodes of the chirp module of the chirp service that I've got, this process will only run on one node. This, as I said, a simple way to do this would be using Apache Kafka or something like that. With Kafka, you can do group subscriptions. All you need to do is say, this is the ID of my group, and then you can have all your nodes at once subscribe, and the events will usually only go to one, but they will be guaranteed to go to at least one of the nodes. So what else do I need to do? I think that's all. If I now go over here, we should see some reloads. I've changed a few services, and something's compiling there. This is a fairly new service, by the way. For some reason, on my Mac, it takes a while to detect changes, and I need to find out why that is. When I do this on Linux, it's all instant and makes for a much better demo. So we should see everything working. If I add a new chirp, let's say I like that. Now if I refresh, it still says 0 likes, and as I mentioned before, this is actually a good example of how it is eventually consistent. The method that it's using to store this and publish this event stream is using a built-in Akka streams thing where it uses a Cassandra feature to get the events, and these actually end up taking a few seconds to get through. So that's now updated to 1. So we can see that that is definitely now asynchronous. If it was synchronous, it would have been instant, but it's definitely asynchronous now. Like if you're using Kafka, it should be instant. So we've now implemented our hopefully more resilient service. Let's try and kill it. So I've just killed it, just make sure that that has reloaded. Yet we can see some exceptions in our log, because when we subscribe to our service, it's failing. You can see that it's killed there, and you can see our supervisor is going to try restarting it later. But our chirps are still there. So our like service going down, we can actually see here, if I click like, it doesn't show me who's liked it. Nothing happens when I click the like button. So it's definitely, the like service is definitely down, but our system is now resilient to that. Okay, so how much time do we have? Okay, we've still got 20 minutes. So the next The next thing that I talked about before about a technique for removing synchronous communication is to communicate through the client. Okay, so a client can cache data, especially if it's a mobile device. Mobile devices will often cache a lot of data, and so they rather than the server having to go and get everything, the mobile clients can actually tell the service a lot of what it needs to know already. But browsers can also cache a lot using local storage, and that's what I'm using today. Client can use their own cache as fallback. So you can either have the client go out and, okay, at the start of the session, go and get all this stuff and then just trust that. Or another way to do it would be to expire that, or even on every call go out and get it. But if it fails, then just fall back to the own cache. Okay, so here we've actually also got an activity service. This is the thing that aggregates all the chirps from different streams, and currently, it goes to the friends service to get the friends first. It's a synchronous call. And then it goes to the chirp service to get all the chirps for those friends. And of course, if the friend service goes down, activity goes down. So let's get rid of that call to the activity service and instead just go directly to the chirp service. So if the client, as long as the client knows who all the friends are, then it can go to the chirp service for that. Of course, the client is still going to go to the friends service at some point. And so I need to be careful in my demo to not hit refresh, because otherwise it won't be able to hit the friends service when I need it to. But something also to be aware of here is we've also reduced the load on friends service, because the client only needs to go to the friends service once and then can keep on using that later. Whereas in this other, going directly to the activity service, you would every time you went and viewed the activity stream, you'd make a new call on the friends service. So let's just have a quick demo of what this looks like. I will unkill my like service. And I'm using React here. You can see here for my activity stream, I'm calling this create activity stream, which is going to our activity service. When I view the likes for a single user, I've also got this call here, which simply gets the stream for a single user. I'm going to make a similar function down here that is able to do it for multiple users. So we pass in some friend IDs, we go to the stream, and we tell it the IDs of the users that we want. This, by the way, is implemented using WebSockets underneath. So then in my activity stream, instead of just going to the activity service, I need to go and from the local storage, I get the current friends. And I also add myself to that because I also want to see my own tweets. And then I can replace this with create friend stream. And I'll pass those friend IDs. And so now when I go to the chirp service, we'll just check that it works. Maybe a little time. Is our like service back up? Yep. So chirp is working. If I go back to the feed's still working. What happens if I kill my feed? Actually, I should have demonstrated what happens if I killed my feed before I made these changes, but you can imagine what would happen, the feed wouldn't work. So we kill the friend service. And so now that's killed, wait for that to reload. If we go back to the feed, it's still loading. We know the friend service is down is because it hasn't been able to load the full, it's just using the username rather than the full name of the user. And of course, if I actually hit refresh, it's unable to log me in because that depends on the friend service. So, but we're still able to consume the activity stream then without having the friend service running. Now, probably a better demonstration of this, I missed some animations there, is in client authorization. I was going to do this as the original demo, but I realized it'd be way too much code and stuff like that. So the idea is, rather than, let's say we wanted to only let people like a chirp or view a chirp if they are friends with that person. So this would mean going to the friend service every single time anything was done pretty much in the system, making the friend service a single point of failure. So instead of doing that, we can use authorization through the client. Now, how can you use authorization through the client if the client is the thing that you're trying to protect your system from, right? You don't trust the client, which is why you're using authentication and authorization. So how can you send the authorization through the client? The way to do it is to use authorization tokens, and a great implementation of that is to use JSON web tokens. And so the idea is whenever you load an entity from a service, that service might, at that point, at this first point, check, okay, you're friends with this user, so you can load this. So the friend service may send you a token saying, yes, you are friends with this user, and it'll sign that. It'll say the friend ID and who you are. Might also put a timestamp in there so that that token can expire. And it'll use a secret of some sort, either RSA or a shared secret. So then when I do an action on anything to do with that friend, if I like their chirp, if I go and try to view their feed, if I go and try and whatever I want to do with that user, mention them, I'll send that token through with that action as maybe an authentication header or part of the request. And so then the receiving service can consume that and can verify the token, say, okay, this token says that this person is friends with this person, the signature matches, so I can trust it, so therefore I know that this user is able to do this action. It doesn't have to make a request on the friend service. It's able to know that without making a request on the friend service, so it's completely isolated from the friend service. And this not only means that if the friend service goes down, the authorization can still be done, it also means that you've taken a hell of a lot of load off the friend service. And so that's pretty much concludes my presentation. You've seen Lagom today. If you want to try it, you can go to lightbend.com/Lagom. I also really recommend reading Jonas Bonier's Reactive Services Architecture. And this is a mini book published with O'Reilly about architecting reactive services that pretty much underlines everything that I've said today plus a bit more. It's got a section on persistence as well and how persistence should be done in microservices. And also this was, I guess, the driving principles behind the implementation of the Lagom framework. So thank you all for listening to me, and I think we'll open it for questions. We'll have a microphone being passed around, so if anybody has a question, please raise their hand. Yep.
And just a question on ordering, because the ordering of events can be important depending upon your domain.
Yep.
When you're working in a multi-data center type of application, what are your thoughts around how you can manage that and the updates of your entities based off of the ordering of events?
So if you have an absolute ordering where all events must be in the right order compared to all other events, then the only way to handle that is in sequence. And that probably won't scale because it means you can only have one node during the processing. And so you'd need to rethink your domain. However, usually what you have is only events for a certain entity or a certain group of entities are ordered. In that case, you can partition your events into topics associated with the partition for the events. And then you can have multiple nodes consuming different partitions. And then within each of those partitions, things will be in order, but things might be out of order otherwise. Another thing that you can also look at doing is if we were to put a timestamp on when the likes were last updated, and we were to trust that timestamp for ordering, then we could say only update our table if the timestamp is later than the last one. So there's a few different things that you can do there. Ultimately, if ordering is critically important and there's only one order and it's all related, you've really got to rethink your domain model there in order to ensure that it can scale. Any other questions? Okay, one more.
Since you're working with events, how do you actually check the state of your application if you have to deal with the chain reaction of events?
So you actually saw then, when I published my like events, I actually went back to the like entity so that was an event source entity that stored the current likes. To be able to send the current count. Event sourcing is one very good way of actually working with the state of the application. The idea is your events, I guess, each event corresponds to a particular entity, and then you can hold that state in memory, persist snapshots if you need to. If there's too many entities and it's not fitting in RAM, then you deactivate entities that haven't been used and reactivate them by replaying the events when needed.
Just a question about Lagom, because I don't know it that much.
Yep.
So when you have to update a service and you're working with entities, does Lagom take care of like draining out the existing service before rolling out the new one, or something that you have to do yourself, kind of as part of the upgrade process?
Draining what in particular?
Well, so you have a service that represents, and the service is working on an entity, right? Yep. And you're going to roll up a new instance or new version, doing an upgrade on that service, right? So yep. You don't want to be taking updates across both instances of that service for the same entity, right? So I'm just wondering, is that something that Lagom or Lightbend manages?
I guess it depends. It depends on the application in each case. So if you have event-sourced entities, each entity is pinned to one node. And so you might have some nodes on the old version, some nodes on the new version. Mm-hmm. The event entities in event sourcing internally are consistent. So you'll just have some entities using the old version of the logic and some are using the new.
Okay.
But when you're publishing events across many things, I guess you have to make sure that whatever that you upgrade, everything that's going to receive those events, if they need changes before the new events are published, that would be something that you probably have to manage manually.
Okay, thank you. Thank you.
Okay, great. Well, thanks for listening to my talk, and